Hello, welcome to this video on solving trigonometric equations for AP Precalculus. We're going to go ahead and look at our good old trig functions, and we're going to put them in equations and go ahead and solve. So, without further ado, let's go ahead and get into it. So for this lesson, we are learning to solve trigonometric equations, and in order to be successful, you're going to have to know your unit circle angles, the values of sine and cosine of these angles, which are your y and x values respectively. You're going to have to be able to solve linear and quadratic equations, so we'll look back at some solving techniques for those types of equations, and as well, you're going to have to go ahead and use trigonometric identities to rewrite a trigonometric function in terms of sine and cosine, because that's what the unit circle gives us, our x and our y values, which are cosine and sine respectively. Okay, but not all equations are going to be given in sine and cosine. We know we have the other four. So let's go ahead and revisit here our trigonometric identities. We have our reciprocal identities, so just remember that cosecant of theta, that is the reciprocal of sine theta, and secant theta, that's the reciprocal of cosine. So whenever we're given these two functions, we want to go ahead and rewrite them in terms of sine and cosine. You're just going to take the reciprocal and then change the function to sine theta or cosine theta. Now, we also have the quotient identities, which we'll use over here. We have tan theta is equal to sine over cosine, and cotangent theta is cosine theta over sine theta. However, I will advocate when solving tangent and cotangent equations that you rely more on your knowledge of the function itself. That tan theta almost looks very, very similar to a y equals x cubed function, right? And you have your main values here, 0, 0. You have negative pi fourths, negative 1, and pi fourths, positive 1. And we have some other values in between. Just remember the smaller value goes to the smaller angle, pi 6, and the bigger value goes to the bigger angle, pi thirds. Cotan theta, again, if you're in my class, we just graph this function. So just remember that you have an asymptote here at 0 and another asymptote here at pi, and we have some values here at pi halves. So we have 0, at pi fourths, positive 1, and at 3 pi fourths, negative 1. Okay, so with those functions, I recommend relying on those functions. Okay, so here's some general steps in order to solving a trigonometric equation. Really, what you need to do is just replace the trig functions with x's. If you get freaked out with trig functions, just simplify it by making them a different variable, and then usually that structure will really come through and you can know how to solve it. So the two types of structures that we're going to see are a linear structure, and this is when we have one trigonometric expression to the first power. You're just going to undo operations to isolate your trig function, and then you're going to use your knowledge of the unit circle in order to solve. The quadratic structure, this is when you have at least one trigonometric function to the second power, or has a product of different trigonometric functions. So what you're going to do here when we have multiple trig functions in the same equation that are different, or one has power of 2, you're going to go ahead and write the equation in standard form, and just remember that your standard form will look similar to this: y equals x squared plus x plus c, some constant, and you're going to use a quadratic strategy. Now this could be the square root property, where if you don't have a linear term, you just set it, you isolate your x squared and take a square root, or you can factor this, right? So we can use a product sum method or factoring by inspection, any of those methods in order to figure out how you can break this down. Okay, and then lastly, you'll use your unit circle knowledge to go ahead and solve those equations. All right, so let's go ahead and check out our very, very first equation. Now, the instructions, super important because they're going to tell you where can your answers exist. The first type of prompt that we'll encounter here, they'll say solve over the interval 0 to 2 pi. So this is just in the unit circle, the first revolution. 0 inclusive, so if we ever have a situation where is it angle 0 or is it angle 2 pi, you use angle 0. 2 pi here is excluded. That's what the parenthesis means. We leave out 2 pi. So here's example number 1. It says sine of x plus square root of 2 is equal to negative sine of x. So here's what I'm going to do. This is a linear structure. I'm going to combine my sine of x terms, sine of x plus sine of x here. These will cancel, and we get 2 sine of x plus the square root of 2 is equal to 0. That's a 0 on that side. Okay, and then now what I'm going to go ahead and do is I'm going to isolate my sine of x. I guess I could have moved the sine of x to this side, but I'm a sucker for keeping my main function, the coefficient, positive. Okay, so I'll move that over. We get 2 sine x, switching to red, I guess, equals negative root 2. And then we'll go ahead and isolate our trig function by dividing both sides by 2. So here's what we get. We get sine of x equals negative square root of 2 over 2. Now, you have to go ahead and solve this using your knowledge of the unit circle. So if you have a unit circle handy, you can go ahead and look at the unit circle and just see, okay, where are my y values? Negative square root of 2 over 2. And you can just do that by inspection. Now, this is not optimal and not, really efficient enough for the AP exam or just, general approach. You need to have kind of knowledge of where your sine value, which of course we know is our y value. Where is our y value? Negative square root of 2 over 2. So this is just screaming pi fourths. We have a pi fourth angle here, so we can say theta, or actually it's not theta. Get your variables right, Schwarberg. X equals, this is a pi fourths, okay, and we're in the southern hemisphere. For our y values, that's negative, so that's going to be 5 pi fourths, comma 7 pi fourths. Okay. All right. Not too bad. Not too bad. Okay. So let's go ahead. Here is a practice example. I'd like you to go ahead. Pause me. Shut me up. Pause me. You try this, and then I'll talk through the example here in a moment. Make sure you pause me. This is how you get your feedback. You can try and make mistakes, and then when you see your mistake, pause me again, fix it, see if you got it right. Okay? Try this one. All right, hopefully you went ahead and tried this example. What we're going to do first is we're going to add cosine of x to both sides. Add your cosine of x, and we get 2 cosine of x is equal to 1. We'll divide both sides by 2, and we get cosine of x is equal to a positive 1/2. So this is where your x value is equal to 1/2. Again, your unit circle or your left-hand trick. I'm going to put down my... Well, the finger that makes my x value is 1/2, right? So that's going to be this finger here. So my x value is a 1, and this angle here is pi thirds. So x is equal to pi over 3. That's quadrant 1, and x is also positive in quadrant 4. So this is going to be, is this 5 pi thirds? 5 pi thirds, 1 less than 2? Yes. Yes. All right, did you get it? I got it. Yippee skippy. Okay. Let's go ahead and let's look at an example where they don't give us the restrictions. So notice how they don't say here, on the interval 0 to 2 pi. They say for all values of x. All infinitely possible answers. Yes, you're going to be writing answers forever until you die. No, I'm just kidding. There's a quick and easy way to do this, and I'll show you that here, okay? All right, so let's go ahead and solve this equation. Note we have a quadratic structure here, power of 2. So I have to take care of that power of 2 one way or another. And what we're going to do first is we're just going to, here I'm going to use the square root property. Square root. And the reason I'm doing the square root property is because I don't have a linear term. I don't have like another tan x, so I'm not going to factor it. It's not like a trinomial structure. So let me move this 1 over to the other side. Plus 1. And we get 3 tan squared x is equal to 1. And we'll isolate our tangent function. Tan squared of x is equal to 1/3. And we're going to go ahead and take a square root. Now, a couple things happen when you take a square root. One is that you're going to get a positive and a negative answer when you're solving. So we have tangent of x is equal to plus or minus, and I have the square root of 1/3, just like this. Now I'm going to simplify this. This is plus or minus the square root of 1 over the square root of 3, which we all know the square root of 1 is just 1 over root 3. Now this may or may not look familiar to you, but this form it might not ring any bells. We're going to go ahead and rationalize this. And when you rationalize this, multiplying the top and the bottom by the square root of 3, you get the square root of 3 over 3. And lo and behold, that value should ring some bells here. Okay? Positive and negative square root of 3 over 3. So, where does this happen? Where does this happen? Again, you can go ahead and put sine over cosine, and you can kind of deduce this value. But if you have knowledge of your tangent function, that it's a monotonic, strictly increasing function, you'll know that this is the smaller value compared to just the square root of 3. When compared to square root of 3, right? This one's larger. This one's larger. That gets the larger angle, the pi thirds. So this is a pi 6. This is a pi 6 angle here, okay? So what we get here is x is equal to, we have pi over 6. And then notice I also have a negative. I have a negative value here, okay? So this is going to be x is equal to 5 pi over 6. 5 pi over 6. So I have the positive value, okay, the positive value, pi over 6. And then I have a negative value here at 5 pi over 6. And you may be saying, hey, what about quadrant 3? Hey, what about quadrant, I guess this is quadrant 2, so quadrant 4. Quadrant 4. Well, here's what we're going to do. I need to account for all values of x. So the positive value, this is going to repeat. Now think about the period of pi. This is going to repeat every period. So plus pi k, let me make sure I'm writing this right, plus pi k, right, where k is an integer. Where k is an integer, okay? And the same thing for the negative value. The negative value is going to repeat every pi value, k, where k is an integer. And you can be super bougie. Let me go ahead and let me see if I still got my, where k is an element of the integers. This is the math. Yeah, I'm pretty sure I wrote that right. If I'm not, any math majors out there, if I wrote this wrong, let me know. I'm slipping 10 years post undergrad. Oh no, it's probably more than that. Probably 11 years post undergrad. Okay, so there you go. Here's a practice example. Go ahead, pause me, and try this example. All right, hopefully you went ahead and tried this one. This is a matched pair example. It looks exactly like the last one. We'll go ahead and add the 3. And we get 4 sine squared of x is equal to 3. We'll divide by 4 on both sides. And you're like, what? This doesn't look anything like the last one. Well, you got to take a square root of both sides. And we get sine of x equals plus minus. Do you remember the plus minus? Square root of 3 over 4, which is plus or minus the square root of 3 over 2. And so hopefully this looks really, 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 really familiar. Square root of 3 over 2. Okay? If you didn't get this, make sure you pause me now and you try to use your knowledge of the unit circle to come up with the answers. I'll post the solutions here in a second. But your angles, this is your y value. Where's your y value? Root 3 over 2. You want your y value, again, this is the pi thirds. Here's my y's. I have a 3 in the numerator. Root 3 over 2. So the angle is going to be x is equal to, so for the positive angle, this is pi thirds. This is pi thirds. And this is going to repeat. This is going to repeat every 2 pi k, again where k is an integer. where k is an integer. As well as we have our negative angle, which our negative angle is going to occur at 4 pi over 3 plus 2 pi k, where k is an integer. Does this account? I don't think this is accounting for the second quadrant. I'm going to say, I don't see this in my notes, but I'm going to add here, you should also have 2 pi thirds plus 2 pi k. And I feel like you should also have x equals 5 pi thirds plus 2 pi k. That accounts for all of your angles. I didn't do that in the last example because my pi period accounted for all of them. Here, 2 pi, that's one trip around the unit circle. I don't think that accounts for all of those values. Okay? All right, so 4 answers here. 4 answers. Bloop, bloop. Didn't see that curveball coming, did you? Okay, but if you had the general idea, that's good. That's good. All right, let's look at another example. This time, notice I have mixed functions. What? You can mix your trig functions? Oh yeah, I did it. Okay, so here's what you're going to do. This is, believe it or not, this is a quadratic structure, and I'll show you kind of how and why here in a second. But what I'm going to do is I'm going to move everything over to one side. I'm going to ship this cotangent over to this side. Okay, minus cotan x. And you may see it like that, or you may see it like this. Cotan x, cosine x, without the parentheses. Actually, I've never seen parentheses like that. Okay, and you may be like, what? It doesn't combine with that cotangent? No, because it's multiplying with this cosine, right? And, ooh, there's the lights. So, how we're going to go ahead and solve this is I need to pull this cotangent away. I need to pull the cotangent away from this function. So what I'm going to do is I'm going to factor out a cotangent. And I want you to see this kind of structure. If cotangent was an x and cosine was a y, we have this structure here. Okay, let me put this in red. Maybe you should see this structure. And what we're going to do is just factor out a GCF. I'm going to take out a cotangent, factor out the cotangent x, and what leaves behind is cosine x minus 1. All right, I took away a cotangent x here. So if I redistributed this, multiply that cotangent x in, wouldn't I get this? I would. So what we get here, now using the zero product property, is I have two possible equations. I have cotangent of x is equal to 0, and I have cosine of x minus 1 is equal to 0. So, cotangent of x, I'm going to purely rely on my knowledge of that function and what it looks like. And I'll go back up to my initial sketch over here. Hopefully you sketched this with me, right? When your teacher writes something down, you should write something down. So, here's cotangent of x, and our function is at 0 at pi over 2. Pi over 2. I'm never going to remember that, Schwarberg. Never remember that. Okay, or just think about it as cosine x over sine x equals 0, and that's going to happen when your numerator is 0. So where is your numerator 0? At pi over 2. At pi over 2. Okay, and I have to account for all the values, so this is going to be plus pi k, where k is an element of z integers. That bougie z right there. That means integers. 1, 2, 3, 4, 5. Oh, don't forget about the negatives. Negative 1, negative 2. And then over here, we're going to solve. I'm going to add 1 to both sides over here. And we get cosine of x is equal to 1. Cosine of x is equal to 1. Okay, so I'm going to go ahead. I'm going to solve this. This gives us x is equal to, cosine of x is equal to 1 at 0. Plus 2 pi k. Plus 2 pi k. Again, where k is an integer. All right. Let me check my notes. Did I get it? Got it. All right. Here's a practice problem. Go ahead, pause me, try this one. And I think this should do it for this part of the lesson. So pause me, try this example, and we'll recap. Okay, hopefully you saw you have a couple of the same functions here, but they don't combine. I'm going to go ahead and subtract that 2 sine x over, that's a subtraction, and this equals 0. And what we're going to do is we're going to take a GCF, factor out a GCF. So I can take out a 2, I can take out a sine of x, and that leaves me with 2 sine of x minus 1 equals 0. From this, you should have got 2 equations. 2 sine of x equals 0, which means that sine of x is equal to 0, which means that x is equal to 0. This is also at angle 0, plus 2 pi k. And over here, 2 sine of x minus 1 is equal to 0. This gives you 2 sine of x is equal to 1. So sine of x is equal to 1/2. Notice it's not plus or minus, it's just the positive 1/2. Okay, and this one actually has 2 values. This could be where your y value is 1. That's going to be pi 6 plus 2 pi k. Or it could be 5 pi 6 plus 2 pi k. All right, again, where k is an integer. K is an integer. You may be saying, what's this little symbol here? It just means it is an element of, okay, I don't think it's an epsilon. I'm just going to stop talking before I show how ignorant I am. Sorry guys, I haven't taken set theory in a while. Okay, so where k is an element of the integers. And again, if this is too bougie for you, like I'm never going to remember that, just say where k is an integer. All right. Hey, that's going to do it for this video. There will be a part 2. We need to look at some more types of examples. But again, you're learning to solve trigonometric equations. Hopefully brushed off your knowledge of the unit circles, values of sine and cosine. We solved some types of equations, linear and quadratic. And then we also looked at using some identity. Well, we kind of didn't really do that. We'll get more into the last one, using your trig identities, these reciprocals, in order to solve in the next video. Hope you liked it. Give me a thumbs up, subscribe. Rad Math Dad, out.